Hi, everybody. Welcome to Physics 151, lecture number 12, which is an introduction to forces and dynamics. And dynamics just means any problem that involves forces. I'm going to be using handwritten slides in this case, just to help get this out a little bit faster. So I apologize for the casual handwritten nature of the slides. First, let's define what a force is. So forces, first of all, really put simply, are any sort of physical push or physical pull. And that's it. That's actually a really good definition for what a force is. So when a rope pulls on an object, or if a person pushes on an object, those are all forces. If you think about that, when something pushes or pulls, not only does it have a strength, right, which is the number of pounds of force or newtons of force. We'll talk about units coming up. But also it has a direction that force is being exerted, that push or pull is being exerted. We'll learn that for many forces, there are rules about the direction that they have to act. And whereas for other forces, like the force of a human just pushing on an object, that could be any direction the person desires. Some of the most common forces that we're going to encounter in this class for mechanics are listed right here. Weight, tension, normal, friction, and elastic force, which is the force of a spring or spring-like object. I'll talk a little bit more about each of those now and on the next slide. But there are many other forces in nature. And the two of them that come to mind immediately are electric forces and magnetic forces, which will be used extensively in Physics 152. But we won't deal with those at all in 151. So first, quickly, remember we've already met weight before. We talked about the difference between weight and mass, and weight is defined as the gravitational force of a nearby planet acting on a mass that's either on that planet's surface or close enough to the planet to feel some gravitational force from the planet. Okay. The variable that's used for weight, many textbooks like to use a single variable like this, W, lowercase w for weight, capital T for tension, lowercase n for normal force, lowercase f for friction. I don't know why the T is capital. That's great and fine. If you'd like to use that notation, you will match our textbook and many other textbooks. A fewer number of textbooks like to call all forces F, and then they put subscripts on them to describe which force it is they're talking about. So G for gravitational, T for tension, N for normal. Or sometimes if it's a person, I'll just write F sub P. Or if there are objects that are named or numbered, I'll use the names or numbers of those objects to label the forces. I prefer this first method here, the first column right here, just because I like to label my force vectors with Fs to be clear those are forces. And then you're going to find that we will have so many other letters for other types of vectors that I prefer to use, like V for velocity vector, A for acceleration vector, F for force vector, and then put subscripts on in a descriptive manner. However, this second method, the second column, is really commonly used, so you should be familiar with it. And if you look in our textbook or many other textbooks, that's what you're going to see. Okay. Describing a little bit more about these forces, tension is the pulling force of a cable or rope or chain or anything else that behaves like a cord or a cable. When it is lax or slack, pardon me, when it is slack, there is zero tension in the cable. However, when it is taut, then it pulls inward on each of its two ends with a certain number of pounds or newtons of force. We'll talk a little bit more about that when we get to some examples. Normal force here is a supportive force of any surface that an object is in contact with and pressing against. So for example, this could be when you stand on the floor, the force that the floor exerts upward on you to support you. Or if you're sitting on a chair, it's the upward force out of the chair. If an object is in contact with a ramp, then the normal force will be outward from the ramp. And if an object like a ladder is leaning against a wall, then the normal force will be outward from the wall. So in those cases, the normal force is not up. It's always outward from the surface of contact. Therefore, it's always perpendicular to the surface of contact. So therefore, hence the name normal. Normal in this case is a mathematical synonym for perpendicular. Okay. Friction in the cases that we're going to be dealing with here are mostly going to be contact friction of an object that's either sliding along a surface or trying to slide along a surface. Occasionally, we will deal with drag force, and I think there's a Physics 151 lab experiment that deals with drag force. That is a different type of friction, and there's different formulas for that as well. But both sliding friction and drag, air drag or fluid drag, are resistive forces, meaning that they always oppose the direction of motion. So if an object is trying to slide or move to the right, then friction or drag force will just act to the left. It'll be always the opposite the direction of the velocity vector. And then finally, spring force is if you stretch or compress a spring away from its equilibrium position, then this is the force that the spring exerts trying to return to its equilibrium point. So in other words, restoring it to its original length. All right, and so it'll be opposite the direction of the displacement of the spring, and it'll be along the spring. I'm not going to say anything else about the spring force and friction force in this lecture. Those will be returned to in future lectures. However, let's say a little more detail about these first three forces on the next slide. So every force has a direction and a magnitude. So I did say some of these things already on the last slide, but let's summarize them really briefly. The direction of weight is always downward toward the center of the planet that's exerting the gravitational force. So that's what I mean by downward, is toward the center of the planet. Okay. Now, this is something we haven't said yet. The magnitude of weight is equal to, now remember, if we take the vector hat off of a vector like this, then when we take the vector hat off, that means we're just talking about the magnitude. If we leave the vector hat on, that means we expect magnitude and direction. You expect to see a direction, or you expect to see a full set of components, right? But if we take the hat off, then what we're just talking about is the magnitude. And the magnitude of weight has a value of m, the mass of the object that you're talking about, and times g. Little g, remember, is a positive value. So in the case of the surface of the Earth, it's positive 9.80 meters per second squared, or something very close to that over the surface of the Earth. If you fly above the height of a planet really far, then the local value of little g decreases. And then if you go far away from any planet, distant outer space, the value of little g is 0, and an object has no weight at all. An object's weightless. So if you're far away from any planet, pardon me, g goes to 0, and then the weight goes to 0. Okay. All right, but the mass of an object, I want to emphasize the mass, which is the amount of matter that an object has, never changes. Right? You can move, well, you can change the mass of an object, but moving it from one planet to another or to distant outer space does not change the mass of an object. Right? You would have to add matter to that object or take matter away from the object to change its mass. Tension, again, I mentioned before, it always acts along the direction of the cable, and it pulls inward at each of the two ends of the cable. So it pulls inward to the middle of the cable from the end. So ropes pull on their two ends. They never push. And there's an old saying that you can't push on a string, right? So that's what they mean by this, right? Tension only pulls. So when a rope or a cable or a chain is pulling inward on its two ends when it's taut, when it is taut, so a slack cable has zero tension, then that's the direction. So the direction point is along the cable, right? It's tangent to the cable or along the cable, and it pulls inward from the two ends. There is no formula. Unlike weight, there is no formula for the magnitude of tension or for the magnitude of normal force that applies generically in all cases. Instead, tension and the magnitude of normal force are specific to every particular problem. So it's something that you just have to solve for custom in a customized way on a case-by-case basis. And then normal force, we already mentioned the direction of normal force is perpendicular to the surface, which is what gives a normal force its name. Okay. By the way, we'll talk about units coming up in a few slides. All right, so let's talk about Newton's three laws of motion. Okay, Isaac Newton is known for a number of things, but one of the things, a number of things in physics, and of course, as one of the co-inventors of the calculus. But one of the things that we remember him most for in physics is his articulation of what we call his three laws of motion. And they basically talk about the first two talk about forces and how forces relate to the motion of an object, right? And then the third law of motion talks about the relationship of whenever a force is generated, a second sort of counter force or reaction force must be generated at the same time. And that is deep and fundamental to the universe. So, but we'll save that for last at the end of this lecture. The first and third laws of Newton's laws of motion are just sort of these English phrases, okay? And they go by nicknames. The nickname for Newton's first law is the so-called law of inertia. There are many ways to phrase this in English. Here, I have put it into my own words, and I've tried to the law of inertia, you may have heard it said in sort of common speech as an object in motion tends to remain in motion, and an object at rest tends to remain at rest. And that is the term motion here is a little vague for me. And in fact, we can be more specific than that. So I've reworded that here a little bit to say an object that is moving, right? In motion means an object that is moving will do so at a constant velocity. So constant velocity is actually more informative, right? Remember, velocity is both speed and direction. So constant speed and constant direction. There's a special case of constant velocity, which is rest. That would be a velocity of 0. And when you have 0 speed, there's no direction. Okay. So notice that this second clause here, an object at rest remains at rest, is simply a special case of the first clause, which is an object will remain at a constant velocity, right? An object remains at a constant velocity, and rest is just a special constant velocity of 0, okay? If, and by the way, that is true if there is 0 net force acting externally on the object. However, if there is some sort of net external forces acting on an object, so one or more external forces acting on an object that sum to something other than 0. Okay, so this could be just one person pushing on an object. This could be one thruster on the side of a spacecraft. It could be multiple forces. You could have an airplane that has forces of drag and weight and lift all acting at the same time. If they sum to something other than 0, then we say that the sum of the outside or external forces has a net or total, or some net or some total value. Then what happens? That means then that an object at rest will not remain at rest if that's true, or an object that's at some velocity will have its velocity changed if that is the case. The net of the outside forces must sum to 0 for an object to remain at a constant velocity or to remain at rest. So let's look at this whole sentence one more time. An object in motion will remain at a constant velocity, and an object at rest will remain at rest unless it is acted upon by some net outside or external force or set of forces, in which case these first clauses up here are no longer true. An object that has some net outside force will not be acted upon, will not have a constant velocity or will not remain at rest. In other words, what does that mean if your velocity changes or you are not remaining at rest, which is another form of velocity changing? It means you're accelerating, right? Acceleration is a state of changing velocity. So that's what we're going to see Newton's second law says. Newton's second law just quantifies that for us. It says that if there is a net outside force, it tells us how big the acceleration will be. Or if there's 0 net outside force, it tells us that there is no acceleration. And these are special cases of no acceleration. Okay. So I just have down here at the bottom that when we say net force, what we mean is sum up or add up all of the outside or external forces acting on an object. So sometimes we call that total, sometimes we call that net, sometimes we use this summation symbol right here. Some books favor one of those over the other. I will use all of those notations at different points in time, and they all mean the same thing. They mean add up all of the outside or external forces acting on an object. Okay, so that's it. This is the so-called law of inertia. Now, it's worth pausing for a moment here and notice, although the word inertia doesn't appear in the statement of Newton's first law as I've written it here, this tendency of an object to either remain at rest or maintain a constant velocity, in other words, not speed up, not slow down, and not turn, right? Constant velocity means constant speed and constant direction. The tendency of an object to do that the ability of an object to resist changes in its velocity, right, which includes changing its velocity away from rest. We call that inertia. That's the property that an object has when it resists those sorts of changes. So I can try and summarize that here. Inertia is the tendency of a body to resist changes in velocity, which means either speeding up or slowing down or turning. All of those are changes in velocity. Okay. It turns out that this isn't that a mysterious um, it's not a mysterious quantity. It turns out it's directly related to the amount of mass or matter that an object has. So it turns out we can directly use mass in kilograms as a measure of an object's inertia. The more mass an object has, the harder it is to change its velocity. In other words, the more it will resist changes in its velocity. You can think of this when you go shopping with a shopping cart. When the shopping cart is empty or nearly empty, its mass is relatively small, so it's very easy for you to speed it up or slow it down, or if you're moving with some speed, to turn a corner. However, as you load it up with more and more and more things, especially things that are massive, right? So not stuff that is low mass like bags of popcorn, but stuff that is high mass like maybe cans of chili or big containers of water. Then what you find is that the shopping cart, as the mass increases, it tends more and more to resist being sped up. Or if it's moving fast, it's harder and harder to slow it down. Or if it's moving at some speed, it's harder and harder to turn it. Now, since we're mentioning the term inertia, I want to mention another vocabulary term here, which is inertial reference frames. An inertial reference frame is any sort of setting. So it could be, for example, the inside of a laboratory or the inside of a spacecraft or the inside of a car or a train, in which Newton's law of inertia, Newton's first law, holds true. Okay. So in other words, if you set an object down at rest, and you have no net forces acting on it, right? Maybe just, so the net force on it is zero. Will it remain at rest, or will it suddenly just start to move in a particular direction? So if you think about riding in a car, well, if you think about like riding in a train or a car or an airplane, there are times when you can set something down on the tray in front of you or some sort of table in front of you that's level, release it, and it will remain at rest. Or if you have a little ball, you can give it a little push so it starts rolling, and it will keep rolling at a constant velocity. What must be true in order for that to happen? Well, it turns out that will only usually happen if the car or the train or the airplane is moving at a constant velocity. Okay. So in other words, if the airplane is cruising along at a constant speed of 600 miles an hour in a straight line and it's not banking or turning or anything, right? So the velocity is constant, both speed and direction is constant. Then it turns out that Newton's first law will hold. If you're in a laboratory and if you're in a physics laboratory and there's a table there and you set something down, and when you let it, if you set it down and it doesn't start to move on its own, right? Or you give it a push and it keeps moving in a straight line at constant velocity when there's no net force acting on it, then we would say that that also is an inertial reference frame. Now, technically, our physics lab is on the surface of the Earth, and the Earth, in fact, is rotating. So it's changing its velocity. The velocity keeps changing direction over time. However, this happens at such a sort of gradual and slow pace that for most intents and purposes, we can neglect it. However, there are experiments you can devise so that you would notice that the fact that the room that you're sitting in right now is not inertial. And if you've ever been to a science museum where you've seen a Foucault's pendulum, then you know that that pendulum, left to its own devices over time, is going to slowly rotate the plane in which it's swinging. That proves to you that that room, that point on the Earth, is not an inertial reference frame. If it were, the pendulum would swing back and forth in the same plane forever. Okay. All right. It turns out the big way to create a non-inertial reference frame is to have an inertial frame that is either accelerating or turning. So if you are in an airplane that is taking off or coming in for a landing, in either of those cases, it's definitely accelerating in the forward or backward direction. Or if it's banking or turning a corner, then in all of those cases, if you set something down on the tray table in front of you, it will either suddenly start to roll toward you or away from you or to the side. If you're on a merry-go-round, the same thing is happening. That's a rotating reference frame. And if you set something down, it will suddenly start to move all on its own. That appears to be a violation of Newton's first law, right? Which is that an object at rest should remain at rest when it has zero net force on it. And in fact, well, it's if it were an inertial reference frame, Newton's first law would be obeyed. But the fact that Newton's first law is disobeyed tells you that the reference frame you're in is accelerating or rotating or both, right? Rotation is just a type of acceleration. All right. So the long story short, if you know due to a physics experiment or something else that a particular frame of reference is inertial, then any other frame of reference that is moving at a constant velocity with respect to that first frame will also be inertial. Okay, so if you know, for example, that the ground outside is an inertial reference frame, then if you're in a train moving at 100 miles an hour on a straight track, not turning and not speeding up and not slowing down, then that is a constant velocity with respect to the ground, and therefore the inside of the train will also be an inertial reference frame. And the amazing thing is there's no, if you blacked out the windows so that you can't see outside the windows of the train, there is no experiment you could do inside the train that would allow you to determine the speed of the train. Because all of Newton's laws will be obeyed at that 100-mile-an-hour constant velocity just as they would be at rest on the ground outside. The same is true on an airplane. Notice that once the airplane reaches its sort of cruising speed and constant velocity, then there's no experiment you can do at your, at your seat or on your tray table that will have any different outcome than if you did it sitting at rest when the airplane is parked on the tarmac. Okay. That's kind of deep that that is the case. And it's a little scary too, because it means that we don't know how fast we're moving right now or in what direction. And there's no experiment we can ever do that will determine that. But it's also a relief because it also means that, well, then when we do an experiment outside or in the physics laboratory, we don't need to worry about the Earth's rotation or the motion of the Earth around the sun or motion of the sun around the galaxy or any of these very fast velocities that are actually happening right now. Because it turns out that as long as there's no rotation involved, as long as we pretend that those are all sort of straight line velocities, it doesn't matter how fast they are or what direction they're pointed in. Any experiment we do is going to have the same outcome as if we were truly at rest. Okay, back to Newton's laws. All right, so that's a lot about Newton's first law. Newton's second law is actually an equation. And it basically says that if there is net force present, okay, so here is the net or total force over here on this right side, then the object that experiences that net force, right, which is going to be the object with mass m, will experience an acceleration, period. Okay, so notice this Newton's first law automatically flows from Newton's second law. So Newton's second law is this equation right here. And Newton's first law just says an object will have zero acceleration if it has zero net force, right? In other words, if the sum of all of the external forces acting on it is zero, then an object will have constant velocity, which includes the possible constant velocity of rest. But if an object has some net force acting on it, okay, so in other words, if there is one or more forces that do not balance out, that add up to some net amount, then an object will A, have some acceleration, and B, the direction of that acceleration will be in the direction of the net force. Okay, and why? Because this mass here is always a positive quantity. So the acceleration will never be in the opposite direction of the net force. And because it's a scalar multiplication, the acceleration can never be in any other direction other than the direction of the net force. So once we know the direction of this net force here, we automatically know the direction of the acceleration and vice versa. If we see an object accelerating, we know the direction of acceleration, we can then immediately tell the direction of the net force as well. Okay, so these two directions have to match. Notice also the proportionality here. Notice that the larger the mass is, the less acceleration you get for a given amount of net force. So suppose an object is experiencing 100 newtons of net force, right, or 100 pounds of net force. Then the more massive an object is, the less acceleration will result. If an object has a mass, if it's 100 newtons of force, if an object has a mass of, let's say, 1 kilogram, then it will have 100 meters per second of acceleration. If it's the same amount of force, but an object has 10 kilograms, then you get 1/10 as much acceleration. And if it's 100 kilograms, you get 1/100th as much acceleration for the same amount of force. All right, so that's important to remember. If two objects are acted on by the same force, the more massive object will have correspondingly less acceleration. Does that make sense? Yeah, because mass is our measurement of inertia, and inertia is sluggishness. It is resistance to acceleration. It's the sort of opposition that an object has to being accelerated. Now I say down here more famously, this equation is written sort of this way. Net force is equal to mass times acceleration. So F equals ma is the famous equation that everyone learns as Newton's second law. And I'll talk about the units that must result from this in just a moment. But the reason I wrote it this other way first is because this first way of thinking about the equation is really the way you should think about it from a physics standpoint. Where does acceleration come from? That's what Newton's second law is saying. Where does acceleration spring from, or what generates acceleration in the universe? The answer is when an object experiences net force, some amount of net external force. That is what causes an object to have acceleration. That's the directionality of causality. Acceleration is caused by net force. It's not the other way around. It is not the case that when an object is accelerating, that causes it to have a net force. No, absolutely not. It is having net pushes and pulls acting on an object that will then cause it to change its velocity. That is the directionality. So that's why I like to think about the Newton's second law this way. This also shows you the inverse proportionality with mass. This shows you how mass is a measure of sluggishness when it comes to acceleration. Okay. However, unfortunately, everybody learns it this other way down here. So F equals ma is sort of the way that everyone memorizes it. And that's fine if you write it that direction. You'll see me write it that direction most of the time as well. Okay, but I want you to mentally think about it the first way. The one useful thing we get out of this second equation down here is units. Notice that the units of force, if we were to ask the question, what are the units of force? Then the units of force must be the units of mass times the units of acceleration. So we can ask ourselves, all right, what are those units in the MKS system? Well, that's kilograms times meters per second squared. Okay, so that must be the unit of force in the MKS system. Now it turns out that has a name that's named the Newton, appropriately enough, after Isaac Newton. Right? And so we use a capital N for that. So notice how the Newton is a compound unit. Okay. So mentally, every time you see Newton, if you want to watch Newtons cancel with other MKS units, you have to replace a Newton by what it is in terms of base units, kilograms times meters per second squared. Okay. All right. I have trouble memorizing what a Newton is. So what I memorize is this formula right here. And if you remember this formula, you can always remember that, oh, the MKS units of force have to be equal to the MKS units of mass times the MKS units of acceleration. And those I have memorized. I remember mass is kilograms and acceleration is meters per second squared. So there we go. Now I remember what a Newton is. I recommend the same thing for you. Okay. That way you don't just memorize what a Newton is as a fact. You memorize this equation, and then you can plug in the units that you know for the more fundamental units. Well, these aren't the simpler units. Plug those into the equation and rederive what a Newton is quickly. Now, if we ask the question, what are the CGS units of force? Well, the CGS unit of mass is the gram. The CGS unit of acceleration is a centimeter per second squared. That has a name that's called the dyne. Okay, and you can see that that comes from dynamics, right? In other words, it means related to force. Okay, all right. And it turns out if you do a conversion calculation, it turns out that one dyne is 100,000th of a Newton. So it's very, very weak. It turns out a Newton is not that strong, and I'll mention that in just a sec, but dyne is then 100,000 times weaker than a Newton. So we're probably not going to use dynes much in this course, but you are likely to come across them at some point, yeah, if you stay in the sciences. So just I want you to be able to recognize, oh, dyne, that's a force unit. Okay, and you can always look it up if you need to later what it is. Finally, the British or imperial units for force are the pound, and of course, the United States is one of the very few countries that still uses this. Well, yeah, yeah, essentially we are. And a pound is about almost 5 newtons. So that's the way I sort of memorize it. Is a pound is roughly speaking, about 5 newtons. It's actually 4.4 something something. It's not exact. So what that means is a newton is about a fifth of a pound. So if you're wondering, is a newton a lot of force? Well, no, it's not, right? If you think about how much force 1 pound of force is, right? Think about how heavy a 1 pound weight is, which is a 1 liter bottle of water. Think about how heavy that is, right? That's 5 newtons already. So 1 newton is like 1/5 of that. Think of the water bottle when it's like 80% empty. Okay, think about how much that weighs. That's about a newton. So a dyne is truly tiny when you think about it that way. Okay, when you get on a scale, let's say you weigh about 100 pounds, right? That means you would weigh about 440 newtons. If you weigh about 200 pounds, you would weigh about 880 newtons. All right, so newton is smaller than a pound. It's about a fifth of a pound, roughly speaking. Okay. So we're going to do a couple sort of examples here to illustrate Newton's second law. And then once I've done the examples, I'll come back to the slides here and we'll finish with Newton's third law. Um, the method I'm going to use for every dynamics problem pretty much going forward will have some of these elements in common. First, I'm going to identify what is my mass m that I'm interested in either calculating the acceleration of or summing the forces on. Okay, and that, so we'll just have to look at the problem and try and decide what is the object of interest. Now, sometimes the object of interest is a system of objects, right? So maybe it might be a collection. If you have like several books sitting on a table stacked together, maybe you want the whole stack to be your mass m. Or if you're interested in just one particular book and the force is acting on that one book, then maybe you just want that one book to be the mass m. Whatever it is, the free body diagram is drawing that object in some sort of very minimalist way, and then using that little sort of, so I'm going to call this, like this object here, I'm going to call that object m. This will be our mass m, whatever that might be. If it's a person, you can just draw some sort of minimal person. Um, if it's a piano, I'm just going to draw a box. That's it. I'm not going to get fancy here. And then we'll inventory all the forces that are external to that object, right? External forces that are acting on that object. They have to be forces that are acting on the object that we're talking about. Okay. Oops. Didn't mean to do that. Okay. All right. So let's sketch the forces. And the whole point of a free body diagram is to help us make sure we inventory and identify all of the forces of interest. So if this object is a book sitting on a table, then I know if I'm near the surface of the earth, it's going to have some kind of weight. So I'm going to call it F sub g, or you're welcome to call that W. If it's sitting on a table, then there must be a normal force acting from the table, and it has to be perpendicular to the table. So I'm going to sketch my force perpendicular to the table. Some people with free body diagrams, they care a lot about exactly where you show the vector originating on the object. I don't care as much. And that's mostly because we're not going to, in this course, we don't have a lot of, we don't care a lot about torques on the object, twisting, twists that result from forces that act on different sides of an object in uneven ways. So it's okay if you were to draw this normal force just like originating on the center of the object. That would be okay with me too, if you were to draw it that way. Um, this is also sometimes written lowercase n, right? And then that's it, right? If there's no other forces acting on this object, no friction, no person pushing, then I'm done. Then my free body diagram is done, okay? If you have a piano being suspended by a rope, then you might say, okay, this piano is near the earth, so therefore it has some sort of weight, right? Or weight. And if it is, let me see if I can extend this this window here a little bit. Okay, good. That'll give me a little more room to sketch this stuff. Okay, so here's my piano. Suppose it's suspended from a rope. So the piano has some sort of weight that acts toward the center of the earth. And then tension. If it's suspended by a rope, then I remember that tension is always directed along the rope, and it always pulls inward from the ends of the rope. So if the rope is directed upward from the piano, then this will be the tension, force of tension, or capital T. And that's it. My free body diagram is done, unless there's other forces that are present. Okay. Um, a lot of the time, these are what I've drawn are very simple free body diagrams, but we'll see in a lot of examples that are coming up that they get more complicated. But it's a handy way for us to keep track of all of the forces that are acting externally on the object of interest. Okay, so remember, it's the forces that act on the object. Never on a free body diagram draw any forces that act on other objects that are not part of your mass M, your object of interest. Okay, there are many other forces in the universe, but we exclude all of them from the free body diagram if we don't want them to go into Newton's second law. We only want to include the ones that are going to go into that net force or total force in Newton's second law. Um, we also, um, I'm sorry, I forget what I was going to say, but that's fine. We'll move on. Okay. If I'm going to use components, then the next step I need to do is to identify the direction of the axes. So usually we often don't need to choose an origin unless we care about absolute position. If all we're talking about are forces, accelerations, and velocities, then the location of the origin doesn't matter, right? And displacements, then the location of the origin doesn't matter. So all we need to really do is identify the direction of positive x and the direction of positive y, so that in the next step, when we break down forces into their components, we know what the angle theta is measured with respect to, right? The angle theta needs to always be measured with respect to this positive x direction. Okay. If we don't care about breaking forces down to their components, then actually you can skip both steps 2 and 3. If all we're going to do is do some sort of graphical addition of the forces in our free body diagram, then we don't need to bother with these two steps. Okay. Or if we're just not going to mess around with components, if we're just going to leave everything as whole vectors, magnitudes, and direction. Okay. And then finally, the step 4 always happens. That's when we take all of our forces, pile them into this left-hand side of Newton's second law, and we find our acceleration. Or in the cases that we know our acceleration, we find the net force. A lot of the times we're going to care about just one component of one force. So we'll have a situation where we just want to find, for example, just the tension or the normal force or something like that, which may only exist, for example, along one component, or may have portions along, probably components along both directions or dimensions, in which case we may need to write everything out in terms of components. And you'll see some examples about that coming up in future lectures, not in this lecture. Okay. If it's a one-dimensional problem, again, you can kind of take the vector hats off and treat everything as positive or negative along that one dimensions, which is essentially the same thing as doing one of these. All right, so to summarize, free body diagram is pretty, you're going to see me start basically every dynamics problem with a free body diagram. If I'm going to head toward using components, then you're going to see me choose my axis and then break down all of the forces in the free body diagram into their components. Otherwise, if I decide I don't need components, I'll probably skip steps 2 and 3. Then I'll use all those forces, pile them into the left-hand side of Newton's second law, and I'll write either one master vector equation, or more often I'll write one or two of these individual x or y component equations to solve for whatever my unknown quantity might be. All right. So let's go ahead and do some examples now. Let me switch my input here. Just a moment. Okay. So if you look at tutorial number 12, I have some example problems there. these first 4 questions are simply to quiz you as a review on what's already been covered in the first part of the lecture. So I will skip those right now. I'll just let you use those as a review from the first part of the lecture. Okay, for question 5 and 6, you're given a free body diagram that's already been sort of filled out. And notice I'm doing sort of to keep the diagram simple, I've centered all the vectors on the center of mass of the object. Although, like I said, most of the diagrams you're going to see that are done a little more properly are going to put the sort of foot of every vector, right? The um, tail of every vector at the location on the object where that force originates from. So the friction force might be drawn down here at the wheels, or the normal force might be drawn at the wheels as well. But just for simplicity, I've just put them all at the center. So the question I have for you is, looking at all of the forces that are acting on the shopping cart, is it accelerating? And if so, in roughly which direction? All right, well, what does Newton's second law say? It says that if we find the sum of all of these vectors, so that's what I'm going to do. I'm going to say find the sum of all of the vectors, right, of these 4 vectors. And then I'll know that the acceleration will be in the same direction as the sum of all the vectors, right? So I'll write it as F total here, okay? So whatever the direction of the sum of all those 4 vectors is, that'll be the direction of the acceleration. All right, well, I'm going to just use a simple graphical method here and put these 4 vectors tip to tail. You can add them in any order because we know that vector addition is commutative. But so I'm just going to pick, I'm going to start here with the normal force. Okay. And I want to try and sketch them the same length. So that's my normal force. And then tip to tail, I'm going to do the vector addition. Now I think I'll add the weight. And now I think I'll add this friction force here, which points to the left. So again, this is all tip to tail, vector addition. And now I think I'll add the force of, this is probably a person pushing if this is a shopping cart, okay? So then I think I'll draw that one here. Oops, that's friction, okay. And then this is the person pushing. And now, to get the net force, I want to start at the beginning of the first vector and go directly to the end of the last vector as the crow flies, right? So this would be the net force, like this. So this would be F total, or the sum of all the forces, okay? And again, these are external, all external to the shopping cart. So if there are any internal forces in the shopping cart, right, between the molecules of the shopping cart or whatever, or some, I don't know, something about the structure within the shopping cart. Or let's say there's a kid inside the shopping cart and they're pushing against the 2 sides equally, or the side and the bottom. All those are internal forces that are not going to affect the overall acceleration of the cart as a whole, right? We only want forces that are acting on it from the outside. And the answer here looks like, if I draw my vectors a little more accurately, I probably would have gotten an answer that's exactly to the right. Yep, it looks like there is a net force exactly to the right. In order for the shopping cart to not accelerate and either remain at rest or continue at a constant velocity, then you would have 4 vectors here that all sum to 0. So for example, what if the person were to push half as hard? Then what we might find is, and also maybe in this case push downward a little bit, well, I bet the normal force would also decrease. So if the normal force decreased and the person were to push half as hard, then we might find is that the net force would be equal to 0, and that would be the case of a shopping cart that is cruising along at a constant velocity, and you would have no acceleration. I'm going to leave number 6 as an exercise for you to try yourself. And it's a very similar question. Okay, let's do a couple more examples on the next page. So if we look at question number 7, suppose that a bullet with a mass of 9 grams starts from rest inside a gun, and suppose it accelerates out of the gun with an acceleration of about 20,000 Gs. What is the net force acting on the bullet? Okay, well, net force, mass, acceleration, sounds like Newton's second law. So we can write Newton's second law. and say that the net force acting on the bullet will give rise to acceleration of the bullet. Okay, and this is the mass of the bullet. So the bullet is the object of interest in this case, right? All right. If we just look at the magnitude of this equation, okay, so magnitude acceleration, magnitude of that force, then we don't need to worry about direction. And the mass of the bullet is 9 grams. Let me actually just write this once more. That's just magnitudes. Times acceleration. The mass of the bullet is 9 grams. Now, if I want my force in newtons, what should I convert the mass to? If you're thinking kilograms are the base unit of mass, that's correct for the MKS system. So I need to convert this. Okay, good. Now I have kilograms. And then the acceleration is 20,000 Gs. Well, Gs is basically like a unit. So I need to make sure I convert these Gs into my MKS units, which are meters per second squared. So I have 20,000 Gs, and I'm going to convert those Gs into meters per second squared. Good. Now I have kilograms times meters per second squared. That'll be newtons when I calculate it. And then I ask my calculator what this is, and I get 1764 newtons. Now, looking at the sig figs, this looks like 2 sig figs for the grams. This is ambiguous. Well, all right. There are multiple choice answers given to me, and they all have 2 sig figs. So let's assume the 20,000 is 2 sig figs. So that's 1,800 newtons or 1.8 kilonewtons. Okay. So either of those would be a good answer. All right. Let's take a look at the next question. So that's just a straightforward application of Newton's second law. Net force. And by the way, this is a sum of multiple forces here, right? This is a combination of the force of the exploding gases behind the bullet, right, caused by the combustion of the gunpowder, minus the drag force from the air in front of the bullet, minus the friction from the sides of the gun muzzle, right? As the bullet slides against the metal, etc. So this is a sum of all of the, and there's weight pulling downward toward the earth. So all of those together are going to add up in some direction that points out of the muzzle of the gun. The acceleration will then be in that direction, whatever direction that is. Okay, and this problem just is asking about the net amount, right? The magnitude. All right, same sort of thing is going to happen here. This iron ball here has a number of forces acting on it. There's the athlete pushing. There is the weight of the ball downward toward the center of the earth. There's air resistance and so on. All of that is going to all add up to some sort of net forward force, right? So this is going to be the sort of total net force acting on that big iron shot ball. So what is the magnitude of that net force if the athlete pushes with a force through some distance of 2.8 meters, starting from rest, okay, and ending up at a final speed of 13 meters per second. So suppose that there's some path through space here that the big iron ball travels through, okay? And in reality, the athlete's not going to push with a constant speed, a constant force exactly, but let's just assume that there's some average value of the force that is essentially equivalent to that constant value. All right, let's first of all say, well, if I want to find out what that net force is, thinking up here to Newton's second law, I'm going to need to know the acceleration and the mass. Well, the mass is given, but the acceleration is not given explicitly. Instead, it looks like I'm given enough information implicitly to figure out what the acceleration is. So first, let's find the acceleration. And this is assuming, let's assume sort of a straight line path, okay? And we'll assume constant acceleration. So if we can assume that there's some average or constant acceleration along a straight line path, then we can apply our equations of kinematics for constant acceleration. So let's do that. There's multiple ways to approach this. I'm just going to try and choose one that only requires one equation. Okay, we know that the shot ball ends at 13 meters per second. It started at rest, and this acceleration was accomplished through a distance of 2.8 meters. So that means the acceleration is about 30.18 meters per second squared. Okay, now notice I'm carrying extra significant figures on my intermediate value. I'm not done yet with the problem, so I don't want round off errors to creep in. All right, now I can apply Newton's second law. Okay, and I'll just use the magnitudes, right? Instead of writing it as a full vector equation, I'll say F total is equal to mass of the shot ball times that average or constant acceleration. Okay, that's equal to 7 kilograms times 30.18 meters per second squared. And I ask my calculator what that is, and I get something that's around 211.3 newtons. Rounding to 2 sig figs, that's about 210 newtons. Okay, so down below is a similar example problem involving this big granite stone right here that's sliding on well, initially it's a frictionless surface during part A. Well, it doesn't matter. It's the net force actually. So there could be some friction force, but there's also the force of the athlete's hand pushing the stone and so on. Okay, and then there's another deceleration of the stone later, and you're asked to find the net force in that case. So this is when the athlete is pushing, and then down there is when the stone is just scraping against the ice due to friction. The last page of this tutorial only has, it basically has no additional calculation required. So all these things are just, they're just asking you sort of conceptual questions about Newton's first law, Newton's second law, Newton's third law, units, weight, the definition of weight, and so on. Okay. All right, so that refers to the other slides we've already covered earlier. Let's go back now and finish with Newton's third law. Okay, just a sec while I switch over. Okay, so Newton's third law. Sorry, we saw how the first law is actually just a consequence of the second law. So I want to just emphasize that once more. It's redundant, right? Once you have Newton's second law, that gives you the first law automatically. In fact, the second law, being that very specific equation, tells you a lot more than the first law. But the first law just comes from the second law naturally. But Newton's third law is really a different thing completely. And this is often nicknamed the law of action and reaction. And the way you've probably heard it in everyday speech is for every action, there's an equal and opposite reaction. Okay, well, the word action doesn't have a very precise meaning for us in our physics class so far. So let's be a little more specific. Specifically, whenever one object exerts a force on a second object, then the second object must exert at the same time, simultaneously, an equal and opposite force back on the first object, okay? So whenever object A exerts a force on object B, then object B exerts an equal and opposite force back on object A. Now equal, let me just be a little more explicit here. This is the magnitude or strength. So in other words, both of those forces have to have exactly the same strength or magnitude, and opposite is the direction, right? So those are the two ingredients of any force vector, magnitude and direction. Okay. All right. Now, so let's just think about a couple examples here, and then I have a couple more pictures coming up. And by the way, this is written in sort of vector math language. That's what it's saying, right? It's saying that the force of object A on object B is going to be equal to the opposite direction of the force of object B on object A. And notice the same magnitude, right? When you multiply by a scalar of -1, the magnitude doesn't change. The vector doesn't stretch or shrink. So put into sort of vector math, that's what this looks like, okay? All right, so if we draw a couple little sort of example sketches, for example, suppose that, oops, okay. Suppose that a person tries to push against a big heavy crate, right? Then the person may exert a force on the crate. So this is the force of the person on the crate. right? At the same time, the crate will exert a backward force on the person. And what can we say about these two forces? Okay. Well, we know that they have to have exactly the same number of newtons. So if the person is pushing with 200 newtons going forward, then the crate must also push back on the person with 200 newtons going backward. And then the directions have to be exactly opposite. So what that means is if the person were to push at a slightly downward angle, so here, if I were to sort of change this diagram a little bit here, what if the person were to push at a slightly downward angle, like that, an angle of like 20 degrees below the horizontal? Well, that means that the crate will push back on the person's hands at an angle that is 20 degrees above the horizontal, okay? If the person pushes harder and increases the force to 300 newtons or something beyond, then the crate will push instantly, push back harder with 300 newtons or 400 newtons or whatever it might be, okay? So the crate will respond with the same force going backward. Now, what if the crate starts to move, right? I mean, you can imagine that everything I've described so far, the crate is so stuck to the ground with friction or whatever that it hasn't budged yet. But suppose the ground is frictionless, or suppose that the person's force is enough to overcome the friction and the crate starts to move. Does this story change? No, it absolutely does not. The Newton's third law says nothing in here about whether the objects A and B are in motion or at rest, right? Or whether they're accelerating or moving at a constant velocity. Newton's third law is always, always true, regardless of the motion of the objects of the two objects that you're talking about, objects A and B, right? So even if this crate starts to slide, so if we start to get some sort of velocity of this crate to the right, then the fact that these two vectors have the same number of newtons will never change. You know, if the person pushes with fewer newtons, then of course the reaction force will have fewer newtons. But otherwise, the fact whether the crate is in motion or not does not affect that fact. Okay. Now, I want to emphasize that when you have an action and reaction force, those two forces are on different bodies. So I've actually drawn, if I were drawing a free body diagram of the crate, if the crate was my objects of interest, right? So the mass in Newton's second law, then which of these forces would I include in that free body diagram? We'll only include forces that are on the object of interest, M. So I would only include this red force right here. But what if I were instead, in maybe a different problem or a different sort of scenario, asked a different question, what if I were to draw a free body diagram of the person? Okay, so what if that person were the object of interest instead of the crate over here? All right, in that case, I would only include the forces acting on the person, and that would be this FCP, this backward force, and I would not include the forward force that's on the crate. So again, the red force is on the crate, so you would only put it in a free body diagram of forces acting on the crate. The green force is on the person, so you would include it in any free body diagram of forces acting on the person. Okay, so you'll never see, as a rule of thumb, you'll never see both of the forces of a action-reaction pair, right? A Newton's third law pair, or is called the reaction force, right? In our textbook, you'll never see both of those two forces in the same free body diagram. It's never going to happen. And suppose the sort of third case I didn't talk about is what if we had the object of interest was the person plus the crate. I mean, that's theoretically possible as well, in which case this would be some sort of like capital M or M2. In that case, both of these forces that I've drawn here are internal to the object. Neither one is external. And the system of the person plus crate, we would never draw either of those forces on the system as an object because those forces are not external to the system. External forces to the system might include things like weight, the earth pulling down on them, normal force from the floor, etc. One last example. What if we had the earth and the moon? And we're going to learn coming up in a future chapter on gravitation. So suppose this is the moon, suppose this is the Earth over here. We're going to learn that all objects, all objects that have mass in the universe exert attractive gravitational forces on all other objects. So suppose if you use a formula we're going to learn later in chapter 6, suppose you use that formula to calculate the strength of the gravitational force of the Earth on the moon. Right? Suppose you actually calculate the magnitude of this force. And we're going to learn it's attractive, so it's exactly along this line that acts between the center of the two objects. Right? What can you immediately say about the direction and the strength of the gravitational force the moon exerts on the Earth? Well, in this case, the first object is the Earth. The second object here is the moon. So therefore, the force the moon exerts back on the Earth is going to look like what? It has to look like. Choose a color here. It has to be exactly opposite in direction. So notice the direction of the first force here is almost downward on the screen, slightly to the left. So I need to have opposite direction for the other force, right, of the moon on the Earth. Okay. So exactly opposite direction. And what about the magnitude? The magnitudes need to be exactly equal. They have to be exactly the same. So notice how I've tried to draw the two vectors the same length on the page, on the screen. Okay. But you might say, well, wait a minute, the Earth is so big. Doesn't it exert a bigger pull on the moon than the moon exerts on the Earth? The answer? What does Newton's third law say? No. Right? Newton's third law says nope. Right? There are no exceptions in Newton's third law here for whether one object is small and the other object is big. That doesn't matter. If one object exerts a force on another object, so this could be like 10 to the 22 newtons or something, I'm just making up a number, then the other object is going to, at the same time, exert 10 to the 22 newtons back on the first object, period. Well, what about the fact the moon's in motion around the Earth? Or maybe they're both in motion around some common center of mass. Doesn't matter. There's nothing in Newton's third law here that says whether the objects have to be at rest or whether they can or cannot be accelerating. Doesn't matter. So whenever you see a Newton's third law looking question, a question about force, action, reaction, force pairs, remember that the magnitude and direction rule, the equal and opposite rule, always applies instantaneously under all circumstances for any two objects that exert either an attractive or repulsive force on each other, right? A push or a pull. All right, I guess I said pull or a push, right? Attractive or repulsive. Yep. And we're going to see this with electrical forces and magnetic forces, and every force in the entire universe obeys this law. Okay, we're also going to find out later this law gives us conservation of momentum as well, but I won't say anything else about that now. All right. So a couple quick cartoons. One, you might ask yourself, well, why does Newton's third law happen? Well, put sort of glibly here, you can say, well, it's impossible to be touched without, I'm sorry, to touch something without being touched by that object in return. So if you touch a table, then the table has to touch you at the same time, right? So what is deeper though than that is the fact that if you push on the table with 5 newtons, the table will push back on you with 5 newtons in exactly the opposite direction at exactly the same time. So simultaneously. And if you decide to suddenly increase the strength of your force to 10 newtons, then so will the table. The table will increase at the same time instantaneously to 10 newtons. Here's some a couple cartoons, this slide and the next slide, which are this is the end of the lecture. And these cartoons just show a whole bunch of forces acting on different objects. So here there are 3 objects in this diagram, and I'll just sort of highlight them here. There's the assistant marked A, there's the sled marked S, and there is the ground marked G. Okay, and this assistant, this is the sculptor's assistant trying to haul a big slab of marble to be carved by the sculptor. Okay. Now notice if the assistant pulls on the sled with a particular amount of force in the forward direction, and we're going to sort of ignore the presence of this rope here, right? Don't worry about the rope. Pretend that the assistant is simply just holding directly onto the sled. If you add the rope, it adds another object, but everything we're saying will still apply. Okay. So if this is a particular number of newtons that the assistant's pulling forward, then the sled pulls backward on the assistant with the same number of newtons at exactly the same time. Okay. Well, then you might ask yourself, if this is always true, if the assistant pulls forward with 100 newtons, the sled pulls backward on the assistant with 100 newtons. If the assistant pulls forward on the sled with 200 newtons, the sled pulls backward on the assistant with 200 newtons. If this happens, no matter how hard the assistant pulls on the sled, how can anything ever move, right? Won't the sled just always keep pulling backward on the assistant with the same equal amount of force, and nothing will ever budge, right? Well, okay, there's sort of two ways to think about the answer to this, and well, two aspects to the answer to this. And one aspect of the answer is, well, it's true. The sled and the assistant actually don't budge with respect to each other. As the assistant hauls the sled forward, oops, as the assistant hauls the sled forward, what we're going to find is, in fact, their separation from each other will remain constant, right? This rope here doesn't stretch. It's not a spring. So it's a taut cable that is not elastic, and in fact, their net displacement with respect to each other will always stay zero. So they don't need to move with respect to each other. What really needs to happen is they need to move with respect to the ground. And if you look at the net force on each of them with respect to the ground, it will be forward. Okay, so the ground will pull backward on the sled with a certain amount of force, but the ground will push forward on the sled. I'm sorry, I said that backward. The sled pulls on the ground backward with a certain amount of force, but the ground will push forward on the sled with an equal and opposite amount of force. Okay. But now we ask ourselves, okay, what's the net force acting on the sled? If we want to ask ourselves, does the sled accelerate? What's the net force acting on the sled? So let me highlight the forces acting on the sled in green. The assistant is pulling forward on the sled with some large amount of force. Let's call that maybe 200 newtons. The ground is pulling backward on the sled with some smaller amount of frictional force, which we might call 100 newtons. Okay. Therefore, the net force acting on the sled is some positive forward force, and the sled accelerates forward. The same is true for the assistant. Okay. And I'll try and highlight his forces maybe in yellow, the forces on him, pardon me, in yellow. The sled is pulling backward with 200 newtons right here, but the ground is pushing forward with more than 200 newtons, right? Something like, let's say, 250 newtons. So what that means is that there is a net force forward on the person, and the person will also accelerate forward. So what do we have? We have the sled accelerating forward. We have the person accelerating forward. Okay, so everything's fine. So yes, things can move in this case. And the only forces we haven't talked about are these sort of backward forces are these sort of forces that are left on the ground. And the ground, I guess I can draw those in red. There's this forward force on the ground here from the sled. There's a backward force on the ground there. So you can see that this one is 100 newtons forward. This one is 250 newtons backward. And what that means is, what do you know? The ground actually has a net force in the backward direction of 150 newtons. Well, what do you know? The ground actually does have some net force acting on it backward. If this were a really tiny planet, then what we would find is that as people and objects on the planet move to the right, so let me try and get a big pen here. As people and objects on the planet move to the right, what we'd find is that the ground will then move to the left at the same time. Okay, this is what happens when if you ever stand up in a rowboat that's at rest and or on a skateboard that's at rest, you try and start moving in one direction, then the rowboat or the skateboard will move in the opposite direction at the same time because the net force is backward. And if this were a really tiny little planet, then what you'd find is that the planet would actually have a net force in the backward direction and accelerate in the backward direction. So if this planet were at rest to start with, not spinning, then as the assistant and the sled try and move to the right, the planet will start to rotate to the left until they stop, and then the planet will stop as well. Okay. The only reason we don't notice this on the Earth, this for us here on the Earth, this part down here is hidden from our senses because the Earth is so massive that when there's a tiny little puny net force of 150 newtons acting on it, no one notices. It's not like all of the buildings nearby all lurch as a result in this backward direction. Okay. But in theory, they are some very, very, very small amount. Okay. Finally, the one last thing, now that I've made the diagram so sort of messy and everything, the last thing I'd like you to notice is notice that this is an action-reaction pair, but but only one of the two was used when I did a free body diagram of the assistant, and only one of the two was used when I did a free body diagram of the sled. And the same is true for this action-reaction pair and that action-reaction pair. That's why this author drew those vectors in different colors. They wanted to show you that within an action-reaction pair, the two forces act on two different objects. So they'll never both appear in the same free body diagram together if they are part of an action-reaction pair. And a lot of times we don't draw like the Earth acting on different things, and we sort of forget that that's there. But that, like, whenever there's a weight, so if you have a weight, well, actually that takes me to the next slide, the next and final slide. Okay, so ignore the right-hand slide for just a moment, and let's talk about this sort of apparent contradiction. When you think about the fact that if you have a heavy object right here, like this bust, and it's of some mass m, so this is our object of interest, and it's resting on a table here, then when we draw a free body diagram of all the forces acting on the bust, we would have a weight, right, acting downward toward the center of the Earth, and we would have a normal force acting upward from the surface of the table. We know that if this bust is at rest, then the sum of the weight and the normal force must sum to zero, right? So we can see that, oh, look, the sum here, the sum of all the forces must be zero because this big heavy bust here is sitting continuously at rest, right? However, that sort of begs the question, all right, I have two forces here that are equal in magnitude and opposite in direction. Are they an action-reaction pair, right? And the answer in this case, well, let's think. What makes two forces an action-reaction pair? If object A exerts a force on object B, object B exerts a force back on object A. What's the object exerting the weight on this statue of Abe Lincoln here? It's the Earth, right? So the action-reaction pair for the weight is the fact that the bust is pulling upward on the Earth at the same time with the same number of newtons. So if all of these force vectors are 100 newtons, let's say, just to pick a round number, then that means that, okay, the Earth pulls downward on the statue with 100 newtons. The statue pulls upward on the Earth with 100 newtons at the exact same time, okay? What about the normal force right here? What if the normal force, the normal force is the force of the table on the bust, right? So what should be the action-reaction force? What should be the reaction force to that normal force? It should be the force of the bust on the table, which will be equal in magnitude and opposite in direction. Why didn't we draw it before? Because this was a free body diagram of just the forces acting on the bust. So we would omit the force of the bust on the table, because that's not a force on the mass m, of the mass of interest, and we would omit the force of the bust on the Earth, because that's not a force on the bust either. That's a force on the Earth. So when we draw a free body diagram, we would only include forces that are acting on the object of interest, the object that's going to go into our Newton's second law, right? In other words, the mass m that's going to go into our Newton's second law. And we would not draw these other two forces that act on other objects, the table and the Earth. Okay, let me clear all this mess, all right? So it was just an illusion that this weight and normal force might have possibly turned out to be an action-reaction pair, but they are not, right? They don't follow Newton's third law, right? Object A exerts a force on object B. Well, weight is the Earth on the bust, and normal force is the table on the bust. So that's three different objects that I've just mentioned, and then it doesn't follow Newton's third law rule. Okay. Finally, we already know that from our previous slide that that a couple slides back that one free body diagram will never contain both of the forces of a Newton's third law pair for that reason. Okay, that concludes lecture number 12. So you'll find that there is a relatively short online homework assignment number 12, mostly conceptual problems and just a few sort of Newton's third law F equal ma problems. And then you can also try the remaining questions on tutorial 12 that I skipped during when I was showing you the examples. So there's plenty more practice questions on there to reinforce the definitions of weight and the meanings of Newton's first, second, and third law.